which materials all this nanostructure shows the potential application in the molecular circuits, computer chips, and quantity science, and biomedicine, and also, yeah, please, this Professor again.
I'm not sure what you want me to answer, okay? There is nothing very special about carbon, and there is nothing so special about graphene carbon nanotubes. It's, we should consider all those materials as part of tools in our toolbox. There are certain elements. I'm not, let me be precise, the only special thing about carbon materials that it has a very strong bond. This is why diamonds and graphene are supposed to be the strongest material of all. This is the strong bond. It also has a consequence that it's chemically very inert material when it's bonded together in any of those forms you have mentioned, but otherwise we have plenty materials in the world: gold, copper, aluminum, silicon. Just those materials you mentioned, it's just an addition which we're not aware of. Dimensionality, this is also important, but dimensionality comes mostly in terms of fundamental physics, because we used to deal with three-dimensional materials for whatever millennia, and now we have two-dimensional materials. We have a lot of tasks on our hands to investigate those. Otherwise, I don't want to be racist. I like all materials.
Doctor, this panel, you have this any question? Any suggestion?
Be racist. I like graphene materials and carbon materials in general because I studied with Professor Guy and he was my PhD mentor. So whatever I'm going to say, he will criticize probably here. But anyway, so I think for those like us who deal with low-dimensional materials and graphene-based materials and carbon-based materials, for us it's like a beautiful sandbox from the fundamental science perspective. So if carbon fiber is a good example of like how carbon-based materials can be industrialized to the huge level that planes are flying because of that. If you now look at the materials from the fundamental science perspective, even diamond, right? You take a diamond, which was always like a jewelry object, right? Now you can do quantum sensors based on diamond. Same with carbon and graphite. If it was just a simple material, now you can use something that for more advanced quantum studies. So from the fundamental perspective, it's beautiful.
Yeah, Professor, when you...
Well, I certainly think in terms of high volume, high application, in terms of scale, without exception, whether it's a 0D, 1D, 2D material, composites is always the first proposed application. However, unfortunately, academia has a lot to answer for in this area because industry doesn't use organic solvents to make composite materials, for example. If you're going to make a composite material, you need to be able to disperse, whether it's a 0D, 1D, or 2D material within a polymer melt. And you'll need to do this at scale. And unfortunately, there's a lot of distance between doing things in solvent and doing things in the melt state. For example, even dispersion within a polymer melt compared to solution is a challenge. You've got to consider not just the dimensionality, but the surface chemistry as well. And there is this dichotomy between, if you, for example, you want mechanical reinforcement, you may need to promote interfacial interaction between the particle and the polymer. So you may need to functionalize the surface. If you're then going to add that to the polymer melt, you need to consider the thermal stability of that chemistry. But of course, if you start covalently functionalizing the surface of particularly carbon materials, you start to disrupt their fundamental transport properties. Yeah? So you can degrade the conductivity, whether it's electrical conductivity or thermal conductivity. However, if you get that right, if you understand how you can mix things in polymer melts at scale, and I agree with the opening comments, we are very much at the bottom of an exponential curve in terms of applications. It's a really exciting time in terms of composite materials. But it's taking quite a while and there's still much to learn to actually apply using industrial processing technology to make composites in the millions of tons. I'm not talking about small quantities. And I think we need to get the terminology right as well when it comes to composites, and particularly graphene composites. Most of the examples you've seen are fundamentally on single layer graphenes, which are typically synthesized by CVD and other types of methods. This is too expensive for composites. If you're going to make a composite, what people do is use a bottom-down approach to produce what's called graphene nanoplatelets or graphite nanoplatelets. And that comes from starting with graphite, where you use different exfoliation technologies to separate and create either few layers of graphene, or perhaps sometimes even more than that. They have slightly different properties because remember your starting material is graphite. It's a naturally occurring material. That's very different, and it's very different to graphene oxide. It's very different to single layer graphene. So we need to be very careful in terminology, because people use a generic term graphene for all of these.
Yeah.
It's not correct. But however, get the dispersion right and understanding how things disperse and melts, and we can make lots of useful composites.
Oh, thank you so very much. Yeah, just the next question is, in the new technological revolution, or also this science revolution in the world, for example, AI, so this topic is in our seminar, which carbon materials should play the more key roles in the scientific field? Yeah, you more the key roles important is in the scientific. The carbon fiber, which is carbon materials. Please, you maybe.
Let me, if I understand your question correctly, which material of carbon is most important? It depends again what you mean. In terms of fundamental science or terms of applications. In terms of fundamental science, there is no any question that graphene is most important material, because on one hand we have three-dimensional materials like graphite. It's too messy, it's too complicated, and hard to dig out beautiful physics out of it. On the other hand, we have one-dimensional, zero-dimensional materials. They are too simple to show many phenomena, and dimensionality too is perfect dimensionality to study many body physics and so on. And for people who are more industrially inclined in this audience, graphene has been a revolution for the last 20 years and continues to be in terms of material science and condensed matter physics and going into this area. If we go a little bit step away, then there are applications. In this case, all materials are good, depending what properties they bring into the table. Buckyball seems to be too simple and too expensive to produce, so competitors are carbon nanotubes and graphene and multi-layer graphene and so on. Again, carbon nanotubes and graphene, they're kind of competitors, but I think graphene offers a lot of advantages, especially it's not toxic material like carbon nanotubes. We are behind carbon nanotubes in terms of industrialization, but there are hundreds already industrial products which involve in graphene. I mentioned before, if you have an electric car, there is about 100 grams of fuel-layer graphene dispersed in your batteries, improving their performance. It's the first step, and so on. Just don't expect magic to happen, to jump from academia into industry, and immediately you have composites and so on. Composites are done, but I'm not sure that graphene can compete with carbon nanotubes in composites. Maybe, maybe not. It's might in the hands of industry, mostly Chinese industry, I have to say.
Yeah, I mean, you something.
So the question is whether carbon materials, graphene, can have any relation to AI directly. So it sounds to me like a good task for a grant proposal. So I have no idea how to answer that question, but let me try. What would I say if I need to write a grant proposal on this subject? So of course there is no direct relation to that. However, if you start thinking, okay, near graphene or carbon materials or 2D materials, there might be something interesting in terms of, say, photodetectors, right? And there is a huge demand for edge AI computing, for like image recognition systems, which are not necessarily related to memory exchange, but you can process this data on chip. So 2D materials, in fact, not necessarily graphene, but hybrid devices, can enable such a technology. And there is a lot of interesting developments going on in the field of smart photosensors and smart vision systems, or say memristors or systems which can integrate logics and memory in the same device. So that can enable a lot of interesting applications for AI, which will potentially save us some energy and some time to do computation.
To answer Professor Gieb's question, I do think that graphene, multi-layer graphene particularly, in rubber, I see huge potential in rubber. And of course rubber is, in our tires for example, is not a very nice material in the sense that its environmental footprint is very, very poor. Carbon black, which makes it black, is derived from the petrochemical industry. And there's an additive package in there which is actually quite toxic. Some of them are shown to be carcinogenic. The increase in the electric vehicle, for example, has increased the weight of your car by 20 to 40%. There's more wear on the tires. Any of these chemicals which are unreacted are getting out. Graphene has been shown, and with some recent work that we've done and with others as well, you can actually, with what's called inverse vulcanization method, you can participate in the vulcanization of the rubber, and not just rubber for tire, without the need for these additives. And so I see really in the sustainable materials market, which is predicted to be over $1 trillion by 2025, you can see graphene making a substantial input. Also in areas like, when you look at sustainable materials, food packaging, for example. If you buy a sandwich in a shop here, you'll typically have maybe 11 or 21 layers. And each of those layers does different things. It might be an oxygen barrier or a CO2 barrier. But each of those polymers, they don't like each other, so you've got to stick them together. What if you could replace this with one polymer that had a 2D material in here, which actually did all of these things together? And this could be recyclable and would be a lot cheaper, in fact. And this is the big issue with these multi-layer packaging. It can't be recyclable. And that accounts for, if you don't know, plastics account for 70% of all plastics goes into packaging. So we can do something about plastic pollution with graphene as well, and other 2D materials also.
I'm always surprised how information about applications is thinly distributed, so even people working in graphene communities, they don't know what's happening in other parts of graphene industry. Especially it's relevant for academics who write grant proposals rather than doing anything useful.
I told you everything will be criticized.
So we're not need to fantasize about application. I already mentioned electrical batteries for graphene, multi-layer graphene, which you can consider as thin flakes of graphite. Another application I'm aware, which is also kind of in full steam, is using graphene in polymers. Instead of tires, they add it to tarmac, to asphalt, and there were for a few years studies in UK on some motorway, 1 kilometer stretch, and then also some airport landing strip was covered. But recently in Italy, they again were very successful, and they covered 250 kilometer stretch of motorway between Turin and Milan with graphene enhanced asphalt. It's all takes time, and how good this material performs, it's a question, because it takes 5-7 years. It's time life of road coverage, but the expectation is that it's increased the cost by 20%, but increased the durability of asphalt by 2.5 times, which is quite a significant achievement if it turns out.
Maybe.
Yeah. But it's 250 kilometers, it's not nothing.
Yeah. As we know, this electronics is based on this silicon materials. Yeah, silicon is based on. Now, next generation of electronics can be based on the carbon materials. Please.
I'm probably not best placed to answer that question.
It will not.
No,
it's going to be based on silicon and silicon hybrid. Yeah.
We have answered this question many times before. I don't know. Dennis knows perfectly the answer. It was a lot of expectation for graphene, but it doesn't have a band gap, which requires switching on or off efficiently. So the consensus is essentially that it's not graphene, but brothers or sisters of this shorthand for them, which people, graphene, when some people like Dennis, me, Kostya, we say graphene, we actually mean often two-dimensional materials. So the consensus is that two-dimensional materials are eventually coming into microelectronics industry. All Samsung, Taiwan Semiconductors, all those companies are closely looking at two-dimensional semiconductors like chalcogenide and so on, sisters and brothers of graphene, not carbon-like, but it's really, I think in this case, academia could do more, especially in growth. No industry wants to do with millimeter sizes or even centimeter sizes. Industry looking for inches and so on, and I think the consensus currently that two-dimensional semiconductors would eventually be in your computer chips.